Greetings, physics students. We're doing another quick and dirty physics video, but this time we're talking about Coulomb's law. Coulomb's law was discovered or formulated back in the 1800s by Charles Augustin de Coulomb, a Frenchman. And what he did is he looked at the forces that different charged particles exerted on one another. And he predicted this, he measured, and then he found an equation that described the situation. So what he found is that the electric force between two particles, let's say charge of Q1 and Q2, first he found that the force is related to the product or the multiplication of the two different charges. Second, he found that the force, the electric force that these particles exert on each other is inversely related to the square of the distance between them. So the further apart they are, the weaker the force is, but it drops off very, very quickly. Now, this equation may look a little bit familiar. So this is all proportional, by the way. There's another constant here, which simply shows that this is proportional. It's not equal to just this part. Now, this equation should look familiar because back when we studied gravity, we saw very much the same thing. We had a gravitational constant, and we saw that the force was related to multiplying the two masses, and then again, the square of the distance between them. So here we have electricity and magnetism and the forces they produce, and gravitation and the force that it produces, and we have literally the same form of equation. What this means is that both electricity and magnetism and gravitation are going to follow the same trends. Now, one of the key things to look at is a comparison of the two constants. If you look at these two values, they are extremely different. Looking at the equations, we would think, oh, okay, same equation, these are going to be fairly comparable. No, they're comparable in how they behave, but in terms of the magnitude of the force, they are very different from each other. Not only is the electrical force a lot greater than the gravitational force because of these constants, it's incredibly much greater. And let's go ahead and take some numbers to go ahead and show that. The value of the electric constant is roughly 9 times 10 to the 9th. The gravitational constant is 6.67 times 10 to the minus 11th. So 9 times 10 to the 9 is an incredibly large number. That's basically 9 billion. And here we have an insanely small number where we're looking at, what is that? We're looking at trillionths. So if you divide an incredibly large number by an incredibly small number, it's going to end up being an insanely large number. So this is going to be roughly, I'm approximating 1.3 or 1.2 something times 10 to the 20. So we are talking about a billion, 100 billion times stronger when you compare the electric force, the electric constant, to the gravitational constant. So although these equations have the same general form, the electric force is much, much stronger than the gravitational force across similar distances. Now, one of the other key things to look at is how the charges behave. As you've read, and you remember from when we studied the atom a while back, electric charges can be either positive or negative. Over here, when we're talking about masses, obviously masses are only positive. There's no such thing as a negative mass. Because charges can be either positive or negative, we have some interesting trends that we need to look at. So if we have one positive charge and a second positive charge, you multiply those together, and obviously we're still going to have a positive charge. If we have a negative charge times a negative charge, the force is going to be positive again. And a positive force means that the distance between the two objects is increasing. So the acceleration is positive, it's moving things away from each other. When the force is negative, they attract. And what we'll see, this goes back to basic middle school multiplication. If you multiply a positive number times a negative number, you're going to get a negative number. So when you have like charges, they will repel each other. I may have just misspelled that. And when you have opposite charges, they are going to attract one another, which was something talked about conceptually earlier in the course and earlier this week as well. Now from here, we're going to switch over from a pen and paper look at things, and we're going to use a simulation on GeoGebra to kind of see these basic trends play out in a simulated format. Here we are in our GeoGebra applet. Many thanks to the author for developing a very nice applet for us to explore these relationships. The actual force is not calculated anywhere in the applet, but what they did is they just took the charges as whole numbers and the distance between the two charges as a whole number and plugged those in. See how they left k just on its own there so we could have nice clean numbers instead of really difficult scientific notation numbers. What we see is we can change the charge by using either one of the sliders. It's negative if we go to the left, 0 in the center, positive off to the right. And we can change the distance between the two charges simply by dragging them around. And what you'll see very quickly here is the greater the charge, the longer the arrow. These arrows represent the force between these two charges. The arrows are pointed away from each other, meaning that this is a repulsive force, which makes sense because here we have a positive charge and another positive charge. So they're going to repel each other. And the larger the charges, the higher the charges, I should say, the stronger the force. See how these arrows just keep getting longer. If we switch things over to and have one of these forces be negative, here we're seeing that the arrows overlap a bit, but again, you see that the magnitude of the force continues to increase. The force gets larger and larger, but this time the forces are pointed in opposite directions, meaning that this is an attractive force. As we change the distance between these two forces, notice as the distance increases, our force decreases. And if we did a little data table, we would see that not only are these decreasing, but they're decreasing very, very rapidly. And that's going to follow the inverse square law, just like what happened with universal gravitation. If you double the distance between the two objects, let's go back and let's pick a nice easy one. So if the distance between the objects is 2 meters, if we double that distance, this force will not be cut in half, it'll be cut in fourths. Okay, that's pretty close. See how we're about 1/4 of the strength of the previous one. If we tripled the distance, it would cut the force down by a factor of 9. Now, if we quadruple it, it'll go down by a factor of 16, etc., etc. I like how the arrows show not only if the force is attractive or repulsive, but they also give you an idea of how quickly the force changes as you change either the charge or the distance. This is a very helpful and simple applet. It'll be linked here in the YouTube video notes. I encourage you to play with it and really learn the trends for yourself and become familiar with them. They will also be provided elsewhere in the course. Thank you guys for joining me for this quick video. I hope this helps you with Coulomb's law and seeing how forces between different charged particles work. If you have any questions, please let me know.